Hello and welcome. My name is Alan, and we are back with more ideas and opinions from Albert Einstein. So, part we're going to read today is called "Notes on the Origin of the General Theory of Relativity." So let's jump into this. Mein Weltbild, Amsterdam, Gerida Verlag, 1934. I gladly accede to the request that I should say something about the history of my own scientific work. Not that I have an exaggerated notion of the importance of my own efforts, but to write the history of other men's work demands a degree of absorption in other people's ideas, which is much more in the line of the trained historian. To throw light on one's own earlier thinking appears incomparably easier. Here, one has an immense advantage over everybody else, and one ought not to leave the opportunity unused out of modesty. When, by the special theory of relativity, I had arrived at the equivalence of all so called material systems for the formulation of natural laws in 1905, um, the question together whether there was not a further equivalence of coordinate systems followed naturally, to say that the least of it. To put it another way, if only a relative meaning can be attached to the concept of velocity, ought we nevertheless to preserve the treating acceleration as an absolute concept? From the purely kinematic prism or point of view, there was no doubt about the relativity of all motions, whatever. But physically speaking, the inertial systems seemed to occupy a privileged position, which made the use of coordinate systems moving in other ways appear artificial. I was, of course, acquainted with Mach's view, according to which it appeared conceivable that what inertial resistance counteracts is not acceleration as such, but acceleration with respect to the masses of the other bodies existing in the world. These was something fascinating about this idea to me, but it provided no workable basis for a new theory. I first came to the I first came a step nearer to the solution of the problem when I attempted to deal with the law of gravity within the framework of the special theory of relativity. Like most writers at the time, I tried to frame a field law for gravitation, since it was no longer possible, at least in any natural way, to introduce direct action at a distance owing to the abolition of the notion of absolute simultaneity. The simplest thing was, of course, to retain the uh, Laplacian scalar potential of gravity and to complete the equation of Poisson in an obvious way by the term differentiated with respect to time in such a way that the special theory of relativity was satisfied. The law of motion of the mass point of a gravitational field had also to be adapted to the special theory of relativity. The path was not so unmistakably marked out here, since the inert mass of a body might depend on the gravitational potential. In fact, this was to be expected on account of the principle of the inertia of energy. These investigations, however, led to the result which raised my strong suspicion. According to classical mechanics, the vertical acceleration of a body in the vertical gravitational field is independent of all horizontal component of its velocity. Hence, in such a gravitational field, the vertical acceleration of a mechanical system or of its center of gravity works out independently of its internal kinetic energy. But in the theory I advance, the acceleration of a falling body was not independent of its horizontal velocity or of the internal energy of a system. This did not fit in with the old experimental fact that all bodies have in the same acceleration in the gravitational field. This law, which may also be formulated in the as the law of the equality of inertial and gravitational mass, was now brought home to me in all its significance. I was in the highest degree amazed with the existence and guessed lie that in it must lie the key to a deeper understanding of inertia and gravitation. I had no serious doubts about the strict validity, even without knowing the results of the admirable experiments of Eotvos, which, if my memory is right, I only came to know later. I now abandon as inadequate the attempt to treat the problem of gravitation, and which, in the manner outlined above, within the framework of the special theory of relativity, it clearly failed to do justice to the most fundamental property of gravitation. The principle of the equality of inertial and gravitational mass could now be formulated quite clearly as follows. In the homogeneous gravitational field, all motions take place in the same way as in the absence of a gravitational field in relation to a uniformly accelerated coordinate system. If this principle field, or if this principle held good for any events, whatever, the principle of equivalence. This was an indication that the principle of relativity needed to be extended to coordinate systems in non-uniform motion with respect to each other if we were to reach a natural theory of the gravitational fields. Such reflections kept me busy from 1908 to 1911, and I attempted to draw special conclusions from them, in which I do not propose to speak here. For the moment, the one important thing that was the discovery that the reasonable theory of gravitation field only be hoped for from an extreme or from an extension of the principle of relativity. What was needed, therefore, was to frame a theory whose equations kept their form in the case of the nonlinear transformations of the coordinates. Whether this was to apply to arbitrary continuous transformations of coordinates or only to certain ones, I could not for the moment say. I soon saw that the inclusion of nonlinear transformations as the principle of equivalence demanded was inevitably fatal to the simple physical interpretation of the coordinates, i.e., that it could no longer be required that coordinate differences should signify direct results of measurement with ideal scales or clocks. I was much bothered by this piece of knowledge, for it took me a long time to see that what coordinates at all meant in physics. I did not find a way out of this dilemma until 1912, and then it came to me as a result of the following consideration. A new formulation of the law of inertia had to be found, which, in case of the absence of a real gravitational field, passed over into Galileo's formulation for the principle of inertia if an inertial system was used as coordinate system. Galileo's formulation amounts to this: a material point which is acted on by no force will be represented in four-dimensional space by a straight line, that is to say, by a shortest line, or more correctly, an external line. This concept presupposes that of the length of a line element, that is to say, a metric. In the special theory of relativity, as Minkowski had shown, this metric was a quasi-Euclidean one, i.e., the square of the length ds of a line element was a certain quadratic function of the differentials of the coordinates. If other coordinates are introduced by means of a nonlinear transformation, ds squared remains a homogeneous function of the differentials of the coordinates, but the coefficients of this function, uh, gm, case of the constant, and become certain functions of the coordinates. In mathematical terms, this means that physical four-dimensional space has a Romanian metric. The timeline external lines of this metric furnish the law of motion as a material point, which is acted on by no force apart from the forces of gravity. The coefficients GUR of this metric at the same time describe the gravitational field with reference to the coordinate system selected. A natural formulation of the principle of equivalence had thus been found. The extension of which to any gravitational field whatever formed a perfectly natural hypothesis. The solution of the above mentioned dilemma was therefore as follows. A physical significance attaches not to the differentials of the coordinates, but only to the Riemannian metric corresponding to them. A workable basis had now been found for the general theory of relativity. Two further problems remain to be solved, however. One, if a field law is expressed in terms of the special theory of relativity, how can it be transferred to the case of a Riemannian metric? Two, what are the differential laws which determine the Riemannian metric, i.e., G, um, maybe that's mu r itself? I worked on these problems from 1912 to 1914 together with my friend Grossman. We found that the mathematical methods for solving problem lay ready in our hands in the absolute differential calculus of Ricci and Levi Civita. As for problem 2, its solution obviously required the construction from the G mu r of the differential invariants of the second order. We soon saw that these had already been established by Riemann, the tensor of curvature. We had already considered the right field equation for gravitation 2 years before the publication of the General Theory of Relativity, but we were unable to see how they could be used in physics. On the contrary, I felt sure that they could not do justice to experience. Moreover, I believed that I could show on general considerations that a law of gravitation invariant with respect to arbitrary transformations of coordinates was inconsistent with the principle of causality. These were errors of thought which cost me 2 years of excessively hard work until I finally recognized them as such at the end of 1915. And after having ruefully returned to the Riemannian curvature, succeeded in linking the theory with the facts of astronomical experience. In the light of knowledge attained, the happy achievement seems almost a matter of course, and any intelligent students can grasp them without trouble. For the years of anxious searching in the dark and the intense longing, their alteration of confidence with exhaustion and the final emergence into the light. Only those who have experienced it can understand that. So, yeah, Einstein kind of talking about how he came to the ideas of the theory of relativity and really understand it. So, yeah. Sorry about that. I know I'm never great at reading these things, but on that one I was especially bumpy. It's been a while, it feels like so. But anyway, thank you for watching. I appreciate it. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite the sources. I'll see you all in the next video. Until then, later.